In example 3, in the notes for absolute value inequalities, we're solving in the form absolute value of A is less than B or less than equal to B. And when the absolute value expression is less than B, we're going to use the and as our compound inequality. So in example A, we're going to start by multiplying both sides of this by 2 so that we can isolate this absolute value expression. Negative 2x plus 8 is an absolute value, and that's less than or equal to 5 times 2, which is 10. Now that the expression is isolated, we can separate this inequality into two separate statements. Either negative 2x plus 8 is a positive, and that number is less than or equal to 10. Could be the case that the negative 2x plus 8 is actually a negative number that is less than or equal to 10. And we're going to solve both of these, and then we're going to join them together with an and. So on this side, we subtract 8 from both sides, and we have a negative 2x is less than or equal to 2. Then we can divide both sides by negative 2, and the x is less than, oh, sorry, we have to change the direction of that inequality. Oops, almost forgot the most important bit there. The x is greater than or equal to negative 1. Now, on our second case, we're going to divide both sides by negative 1, which is going to change the direction of this inequality. So we'll have a negative 2x plus 8 is greater than or equal to negative 10. Now we can subtract 8 from both sides, and negative 2x is greater than or equal to negative 18. Then let's divide both sides by that coefficient of negative 2, and now we get to change that direction of the inequality again. So x's are less than or equal to negative 18 divided by negative 2, which is a positive 9. So our two solutions are x's that are greater than or equal to negative 1 and x's that are less than or equal to 9. Another way that we could write that statement would be to say we want x's that are between negative 1 and positive 9. Right? Those two statements mean exactly the same thing. When we want to sketch our solution set on a number line, we'll have closed circles at negative 1 and at positive 9 to indicate that those endpoints are inclusive. And because it's an and inequality, we shade between those real number endpoints. Because the x's are greater than or equal to negative 1, they shade up. Less than or equal to 9, those shade down. So they meet in the middle. Now let's try example B. So to isolate this absolute value inequality expression, we're going to subtract 4 from both sides, and the absolute value of the quantity 6x minus 3 is strictly less than 15. Now that that absolute value expression is isolated, we can break it into the two possible cases. Either the 6x minus 3 is positive in that expression, the absolute value keeps it positive, and it's less than 15. Could be the case that that 6x minus 3 is actually a negative number, the absolute value makes it positive, and then it is less than 15. So these two possibilities will get solved and joined by an and because they are less than absolute value form. So let's start by adding 3 to both sides. That gives us a 6x strictly less than 18. Then we're going to divide both sides by 6 to get the x by itself, and x is strictly less than 3. Then our other case, we start by dividing both sides by -1, and that's going to change the direction of this inequality. Then we can add 3 to both sides. Now 6x is strictly greater than -12. Then we can divide both sides by that coefficient of 6 to get x, which is greater than -2. So we'll have x's less than 3 and x's greater than -2. We could also write that as x between -2 and 3, right? Those mean the same thing. Or we can represent that solution set on a number line with open circles at our endpoints of -2 and 3. And we're going to shade between because it's an and inequality. The x's are greater than -2, so we shade up. They are less than 3, so we shade down. And that shading overlaps in the middle. Okay, go ahead and try this one on your whiteboard. And when you're ready to check, you can resume the video. So here's our solution to this inequality. 3 absolute value of the quantity 2x plus 6 minus 9 is less than or equal to 15. So we add 9 to both sides, divide through by that coefficient of 3. Now our absolute value expression is isolated. So we'll take the 2x plus 6 and divide it into the two cases. Either the 2x plus 6 in absolute value is positive, it stays positive in absolute value, and is less than or equal to 8. It could also be the case that 2x plus 6 in absolute value is a negative number, and the absolute value bars are what make it positive. When we solve those two different cases, we get x's that are less than or equal to 1 and greater than or equal to -7. So the x's between -7 and +1. We use closed circles on our graph to indicate that those endpoints are inclusive, and we shade in between.